Here's problem 8.8. A 12 kilogram block on a horizontal frictionless surface is attached to a light spring, force constant 0.8 kilonewtons per meter. The block is initially at rest at its equilibrium position when a force, magnitude 80 newtons, acting parallel to the surface is applied to the block as shown. What is the speed of the block when it is 13 centimeters from its equilibrium position? Alright, so we have a mass of 12 kilograms, and we're located at the equilibrium position, so let's call that point A. And we're going to extend this out to some new position. Let's call that point B. So this distance that we extended it was 13 centimeters from the equilibrium position. So x is 0.13 meters. That x is going to also be d, the distance that we extended, under this force P. P is equal to 80 newtons, and the spring constant is equal to 800 newtons per meter. Alright, let's approach this with the one equation to rule them all. Kinetic energy at A plus potential energy at A plus any work done on the system along the way will equal the kinetic energy at B plus the potential energy at B. Everything is on a level plane, so our gravitational potential energy will be 0, but we do have spring potential energy. At point A, the spring is not extended or compressed, so we have no potential energy at point A, but we will have potential energy at B. It's going to be 1/2 kx squared at B. And we start from rest, so our initial kinetic energy at A is going to be 0, but we will have kinetic energy at B, so we'll have a 1/2 mass times velocity at B squared. We have work done along the way. That's the work done by this force P, and it's acting for a distance d, d right here, and they're in the same direction. So this is going to be P times d cosine 0 degrees is going to be the work done along the way. Cosine of 0 is 1, so it's just going to be P times d. Alright, so now we can set this up and try to solve for the velocity at point B. We have everything else that we need to know. So I have that 1/2 mass times the velocity of B squared should equal P times D minus 1/2 kx squared. So if I multiply both sides by 2 and divide by the mass, I'm going to have that the velocity of B is equal to 2pd minus kx squared divided by the mass, or, this is velocity squared, or take the square root now of both sides. So the velocity of B is going to equal 2 times p times d minus kx squared over the mass square root. That's going to be 2 times 80 times d, which is 0.13, minus k, which is 800, times x, 0.13, squared, over the mass, which is 12, divide, or square root everything. And if I do that, 2 times 80 times 0.13 is 20.8 minus 800 times 0.13 squared is 13.52. All that divided by 12 square root. Gives me 0.779 meters per second. So that is our velocity at point B.